Hey everybody, Mr. Antonucci here, and in this video, we're diving into the 2025 AP Stats free response questions. Whether you've already taken the test and want to see how you did, or you're prepping for next year, this walkthrough is for you. We're going to break down what each problem is asking, talk through some of the key concepts, some strategies, some common mistakes, and most importantly, solve the problem for you. Okay, question one gives us a classic box plot comparison, gas mileage for cars from country A versus country B. In part A, you have to compare the distribution. This means discussing shape, center, spread using comparative language such as greater than, less than, and not just listing the statistics. So here's what we would write for the answer to part A. Compare the distributions of gas mileage for the sample of cars manufactured in country A and the sample of cars manufactured in country B. So here's what we'd say. The distribution of gas mileage for the sample of cars manufactured in country A looks to be skewed right, and the distribution for country B being more symmetric. The median of the distribution for country A is 18 miles per gallon, while the median for country B is greater than that at 32 miles per gallon. The interquartile range for A is 8 miles per gallon, while the interquartile range for B is greater at 18 miles per gallon. Country A has one outlier at 38 miles per gallon, and country B has none. Let's look at part B. For the distribution of gas mileage for the sample of cars manufactured in country A, would you expect the mean to be greater than 18, less than, or equal to 18? Justify your answer. So this is a conceptual question, no calculations. So here's what we would get. I would expect the mean for country A's distribution to be greater than 18 miles per gallon, since the median is 18 miles per gallon and the distribution is skewed to the right with an upper outlier. The mean is not resistant to outliers and is greater than the median for data that is skewed to the right. Therefore, I expect the mean to be greater than 18 miles per gallon. Part C, the manager will create a new box plot with the combined data from the sample of cars manufactured in country A and the sample of cars manufactured in country B. What is the range of the combined data set? Justify your answer. So with justification, the maximum of the combined data set would be 40 miles per gallon for country B, and the minimum of the combined data set would be 14 miles per gallon from country A. Therefore, the range of the combined data would be 40 minus 14, or 26 miles per gallon. Second part of problem C, what is a possible value of the median of the combined data set? Justify your answer by referencing the box plots shown. So if we look at the box plots here, we have country A and B. If you notice, country A, Q3, is at 24. So about 75 of the 100 values are less than or equal to 24. For country B, 24 is at Q1, which means about 25 of the values are less than or equal to 24. So for the combined data set, that would mean about 100 of the values are less than or equal to 24, which is half of the 200 combined values. So 24 miles per gallon is a good estimate for the median of the combined data sets. So here we have the answer written out for you. Question number 2. This was a solid question on sampling methods. Here's where a farmer wants to estimate the proportion of cabbage plants damaged by aphids. In part A, this challenged you to critique method 1 of the sampling method. B made you consider bias in selecting row E, which was closest to the river. And part C asked for a description of how to implement a stratified type sample. So here we go with the solution. Part A, explain whether the sampling method 1 is an appropriate sampling method for the farmer to use to estimate the proportion of cabbage plants in the field that are damaged by aphids. So here's how we would answer part A. Method 1 is not an appropriate sampling method because it does not represent the whole field. Since the farmer supposes that plants closer to the river would have greater damage, if the farmer only selects plants that are close to the house, he's likely to underestimate the true proportion of cabbage plants in the field that are damaged by aphids. Now, part B, using sampling method 2, the farmer randomly selects row E and examined every cabbage plant in row E. If the farmer's belief is correct, determine whether the selection of row E is likely to provide an overestimate or an underestimate of the proportion of cabbage plants in the field that are damaged by aphids. Justify your answer. So here's what we had. Method 2 is likely to overestimate the true proportion of all cabbage plants in the field damaged by aphids. Since the farmer's belief is correct and plants closer to the river have more damage from aphids, selecting row E, which is closest to the river, will produce an overestimate. Now for part C, using the information provided in the diagram of the cabbage field, describe how to implement sampling method 3, which requires random selection of one region from each of the rows in A, B, C, D, and E. So this is a stratified type sample where each row is the strata, and then we're going to randomly select one plot within each row. Basically, you have to make sure that you cover a couple things. First, we're going to use a random number generator to get a number between 1 and 5 to randomly select a plot in row A. Then you would go to that plot and inspect every cabbage plant in that plot. Then you would repeat that process for row B, which would be numbers 6 to 10, row C, which is 11 to 15, row D, 16 to 20, and row E for 20 to 25. Then for all the plants inspected, you would record the proportion of plants that were damaged by the aphids. So the thing you have to do is then write all of that out. So I'll put that below. So here we have the answer for part C. So that's it for number 2. Question number 3. This is our probability in binomial setting question. Part A was a straightforward process of finding basic probabilities. Part B took it to a binomial model, and Part C added depth by using binomial methods and then having to explain some things there. That last part required some thoughtful reasoning because you had to discuss expected variability and recognize that 4 isn't actually that surprising. This is the first time you really have to make some calculations on the AP exam. So part I, I'm going to put right here. Suppose one song is selected at random to be played. What is the probability that the song is a rock song? Show your work. Well, we have 1,000 songs total, and 100 of them are rock songs. So that would be 100 out of 1,000, which is 0.1. Part 2, suppose 2 rock songs are selected at random. What is the probability that both songs are rock songs? Here's something you have to consider. It says any song can be replayed at any time, meaning this is sampling with replacement. So you would have 100 over 1,000 times 100 over 1,000, not 99 over 999, which is going to give us 1/10 times 1/10, or 1/100th. So part B, every 1 hour period, 20 songs will be played at random, and any song can be replayed at any time. Mrs. Fay is interested in how many rock songs will be played in a typical 1 hour period. Define the random variable of interest, Mrs. Fay, and state how the random variable is distributed. What is the expected value for the random variable in part B? Show your work. So for part I, we're going to define it as X. You could use Y or W or capital R. Typically, we're going to use capital X, and it's going to be the number of rock songs played in 1 hour. Also, we needed to state how the random variable is distributed. So we need to add that X is binomial with N equals 20 and the proportion of successes equals 0.10. Now, for part 2, the expected count is just going to be the number of trials times the probability of success, which you can get that's on the AP Stats formula sheet. So here we just do 20 times 0.10, which is 2 rock songs. It's helpful to label your answer. Moving on to part C, recall that in every 1 hour period, 20 songs will be played at random, and any song can be replayed at any time. Part 1, determine the probability that 4 or more rock songs in a particular 1 hour period will be played. Show your work. So we would write the probability that X is greater than or equal to 4. Now we can do this on the calculator with the binomial CDF, but remember the cumulative density function always does the probability of that value or lower. We would have to do 1 minus the probability of X being less than or equal to 3. So this is going to be 1 minus binom CDF with N equals 20, P equals 0.10, and X equals 3. This would give you 1 minus 0.867, which is 0.133. So even if you do the binomial CDF on your calculator, you still have to write down the notation there to get full credit. Part 2, suppose 4 rock songs are played during a particular 1-hour period. Does this provide strong evidence that the song selection process was not truly random? Justify your answer without performing an inference procedure. Assuming that this process is random, and there is a 0.133 probability that 4 or more rock songs get played, that would not be surprising because 0.133 is greater than a significance level of 0.05, which is typically the significance level we use when one isn't stated. So we have convincing evidence that the song selection process was not truly random. So I'll write that out for you down here just so you can see it in a concise statement. So there I have it for you. And that finishes problem number 3. So number 4, our full inference procedure. This question focuses on a one sample z-test for proportions. Here, Karen believes her school uses an app more than the national rate of 22%. The task was to run a full hypothesis test. Make sure you do the state, plan, do, conclude, and at the 0.05 significance level. State, we wish to test the hypothesis the null p equals 0.22 with the alternative p greater than 0.22. So remember, based on the context, this is a one-sided test where p equals the true proportion of all high school students at Karen's school who use the app to help them with their homework at least once per week. We defined our parameter in the full context, and we also stated the significance level. Our next step is the plan step. So in our plan step, we are listing the inference procedure we're using, which is a one sample z-test for proportions. And we need to check the conditions. It's not enough to just write random 10% large counts and put a check mark. You need to state how they are actually satisfied. So for random, you would write random sample of 130 students. 10%, you have to show that the sample size, 130, is less than 10% of the 2,000 students at the school, which it is. The large counts condition, you have to show that the expected proportion of successes and failures based on the null proportion of 0.22 are both greater than or equal to 10. You would not use the actual results for the sample there. The next step we're going to do is the actual do step. So for the do step, we need to calculate our z-score, which is the proportion of the sample, so 38 out of 130, minus the null proportion, 0.22, divided by the standard deviation, 0.22 times 0.78, all over the sample size of 130, and this is going to give us 1.99. So the p-value, based on a z-score of 1.99, is going to be 0.023. If you draw the graph, you would have the normal probability, the mean of 0.22, and you'd be up here at a z-score of 1.99, which is 0.2923. That's what the sample proportion would be as a decimal, and we'd shade to the right to show that. And then finally, we have our conclude step where we state our conclusion based on our p-value. Because 0.023 is less than our significance level of 0.05, we reject the null and have convincing statistical evidence to support Karen's belief that a greater proportion of students at her high school use the app weekly than those in the country overall. I'll write that out for you. So here we have our conclusion written out for you, and that concludes question number 4. Jumping into question number 5, this was all about means and distributions of a discrete variable, number of bedrooms. Part A had basic probability and expected value calculations, while Part B moved to a one sample t-test, and Part C included a confidence interval interpretation. So this one tested both your ability to compute and to communicate clearly about inference. So let's jump into Part A here. A house from the sample will be selected at random. What is the probability that a house had fewer than 3 bedrooms? Show your work. So this is pretty straightforward question here for part I. All you have to do is just add the probabilities. You have 0.12 plus 0.22 plus 0.28, which comes out to 0.34. Pretty straightforward there. Part 2, what is the mean number of bedrooms for the sample of newly built houses in 2024? Show your work. So for this one, to get the mean, you just multiply the number of bedrooms by its proportion. So to show your work, you would do 1 times 0.12 plus 2 times 0.22 plus 3 times 0.28 plus 4 times 0.22 plus 5 times 0.14 plus 6 times 0.02. You multiply and add all of that up, and you would get a mean of 3.1 bedrooms. Pretty straightforward there. Part B, Rodney will use a one sample t-test for a population mean to test his belief. In the context of Rodney's investigation, state the hypothesis of the test. So here you have to state the null and alternative hypothesis as well as define your parameters. So the null would be that mu is 2.9. The alternative, mu is not equal to 2.9. We're just looking for a difference, not in either direction specifically. Mu is the true mean number of bedrooms in newly built houses in the country in 2024. I'll write that out for you. So there we have it written out for you. Now in part II, explain in context what a type 1 error would be. A type 1 error is when you reject the null when you shouldn't have. So in the context here, this would occur if the true mean number of bedrooms in newly built houses in the country in 2024 really is 2.9, but the hypothesis test incorrectly rejects the null and finds convincing statistical evidence that the mean is different than 2.9. And there we have it written out for you. Part C, a different researcher, Keisha, suggests using a confidence interval to investigate whether the mean number of bedrooms in newly built houses in 2024 in country B was different from 2.9. Assume the conditions for inference have been met. Using Rodney's data, Keisha calculated a one sample 97% confidence interval to estimate the population mean as 3.01 to 3.19. Based on the confidence interval, what conclusion can be made for Rodney's hypothesis test in part B at the alpha level of 0.03? Justify your answer. Now, one thing you'll notice right away is that 2.9 is not contained in the 97% confidence interval. So since the confidence interval does not contain the null, we would have convincing evidence at the 0.03 significance level that the true mean number of bedrooms in newly built houses in the country B in 2024 really is different than it was in 2017. I'll write that out for you below again. So that's it for question number 5. How'd you do? Jumping into number 6, the dreaded investigative task. This dealt with comparing two means, AM versus PM reading sections. Part A asked us for a conclusion based on a p-value, and you had to interpret statistical significance in the context. Part B was more conceptual, why this was not a paired design. And Part C brought in Cohen's D effect size, where you had to compute some calculations here and interpret how meaningful the result was just beyond statistical significance. And then part D wrapped it up with a deeper dive into how variability affects size and practical importance. So let's go ahead and look at some of this. Part A, the p-value for Stephan's hypothesis was 0.002. State an appropriate conclusion at the 5% significance level for Stephan's test in the context of the investigation. Justify. So here, since the p-value of 0.002 is less than the significance level of 0.05, we would reject the null and conclude that Stephan has convincing statistical evidence that the mean reading score for all children, similar to those in the study, who would read a story at 9 a.m. is different than the mean reading score for all children, similar to those in the study who would read a story at 3 p.m. So there you have part A written out for you. In part B, we had explained why it was appropriate for Stephan to conduct a two-sample t-test for the difference in two population means instead of a paired t-test for population mean difference. The important thing is to understand that the reading comprehension scores in this study came from two independent groups that were created using random assignment. They were volunteers, but the groups were created from random assignments. So the individuals at the 9 a.m. treatment group couldn't be paired with specific individuals in the 3 p.m. treatment group. That's why we needed to conduct a two-sample t-test for the difference in population means. Again, I'll write that out for you below. So there you have B written out. Now, part C has a lengthy explanation of what Cohen's d coefficient is and how to calculate it and what it means. I'm not going to read all through that. We're going to jump right to the question. Part I, calculate Cohen's d coefficient for Stephan's study, show your work. So in this case, d is equal to the absolute value of 15.2 minus 17.9 divided by the square root of 4.12 squared plus 4.43 squared over 2. If you pump that into your calculator, you end up with 0.63. So all you had to do there was calculate Cohen's d coefficient, 0.63. Part 2, higher values of Cohen's d indicate greater practical importance and lower values of Cohen's d indicate less practical importance. Typically, we use the intervals listed in Table 2, right there, to help interpret the practical importance. Based on your answer to Part CI and the information in Tables 1 and 2, describe the practical importance of Stephan's results in context. The difference of means of 2.7 that Stephan got from his study resulted in a Cohen's d value of 0.63. Since 0.63 is in that second interval there between 0.2 and 0.8, the experiment is somewhat meaningful in real life. Now you just have to write that out in a coherent sentence, and I'll type that up for you below. And there you have part 2 typed up for you. There's one more part to this question, part D. Suppose the results of Stephan's study summarized in Table 1 instead had a standard deviation for the 9 a.m. reading scores S1 and a standard deviation for the 3 p.m. reading scores S2 that were both greater than 4.43. Assume the group sample sizes and the means are not changed. Would the Cohen's d coefficient in this new situation be smaller than, larger than, or the same as Cohen's d coefficient calculated in part C? Explain your answer. Well, notice how Cohen's coefficient is calculated. It's the difference in sample means divided by the pooled standard deviation. Now, both standard deviations, if we look back, were 4.12 and 4.43. Now they're saying they're both going to be greater than 4.43. Well, if both standard deviations are greater than 4.43, that's going to increase the numerator here, because you're still dividing by 2, still taking the square root, and still having the same difference in sample means. That's going to result in you dividing by a larger pooled standard deviation, which is going to then decrease the value of Cohen's d coefficient. So we would just have to write that out in a coherent statement, and I'll do that here below. So there you have it. Now, part 2, does the Cohen's d coefficient described in part D indicate that Stephan observed difference in the means in the new situation would have more practical importance than, less practical importance than, or the same practical importance as was originally determined in part CII? Explain your answer. Well, in general, because the lower a Co and D coefficient is indicates lower practical importance, this is going to result in less practical importance. And that's basically what we're going to write here. So there you have it, and that ends question number 6. Now, overall, the 2025 FRQs hit all the big ideas, comparing distributions, experimental design, probability, inference, and communication. So let me know in the comments which question you found the toughest or the most interesting. And make sure you hit that like button and subscribe so you don't miss any more videos that I'm putting out. Thanks for watching, and I'll see you in the next video.